On daily conversation, the term mechanics may loosely be interpreted as how things work. What is the mechanics behind a refrigerator, for instance? That means how a refrigerator works. And a mechanic is someone who has the working knowledge of things. Physics has a much more abstract definition of mechanics. It is the study of how a physical system evolves from one state to another. Whoa. Those are big words. Physical system, states. What are states in physical system? Evolve? Let me illustrate my point. A car is moving on the road. A car is a physical system. Yes, it is an engineering marvel too, but engineering is just physics put into application. So a car is a physical system. The states of the car are then referring to the parameters which are attached to the car. If this were an art lesson, then you might want to refer to the state of the car in terms of its color, which is green. If this were a lesson on product design, then you might be interested in the state of the car in terms of its shape. It is a beetle, by the way. Since this is a physics lesson, let me tell you that physicists refer to the position and velocity of the car as the states of the car. Position and velocity, or momentum if you will. But you probably have not learned momentum before, so let us stick with velocity for now. Once again, position and velocity are the two quantities used by physicists to describe the state of a physical system. So say in our case, at the moment, 1 meter and 2 meter per second in the positive x direction are the position and the velocity of the car respectively. In case you guys forget, velocity is a vector quantity, so it should come with both magnitude and direction. But why position and velocity? What good can these two quantities for? Since the dawn of history, one endeavor remains the greatest and most challenging, if not impossible, and that is predicting the future. For that, humans turn to religion, fortune-telling, science, and even Paul the Octopus. Be it the next World Cup winner, lottery strike, weather forecast, or the up and down of financial market, no less effort are spared by mankind to have a peek to what may happen in future. Movies are produced and novels written inspired by such effort. Physicists are doing the same thing. Of course, we do not rely our prediction on some sort of psychic power or advice from the netherworld. It is unphysical to do so. Instead, we rely our prediction on data and model. Allow me to explain further. Now, we didn't establish this earlier, but in reality, the value of 1 meter and 2 meter per second will not just appear out of nowhere. You see the car coming, you quickly bring out your speed gun, you set up a coordinate system, probably using the nearby lamppost as a reference where you assign the origin of the coordinate system. And voila! At one particular time, let's denote this time t subscript 0, you discover the car at position 1 meter. We denote this position by x subscript 0 in reference to x at t0, moving at 2 meter per second to the right or positive x direction. And we denote this velocity v subscript 0 also in reference to v at t0. What have you done? Well, you just did a measurement or an experiment, and measurement produces data. So you have in your possession data, which you may want to tabulate into something like this. What will happen to the car 2 seconds later? Or to be more exact, what will happen to the position and velocity of the car 2 seconds later? Well, this is where a physical model comes in. Now, by model, I'm not talking about babes and hunks walking down the catwalk. In physics, a model is simply an equation or set of equations which can be used to describe a physical phenomenon, an outcome of an experiment or observation if you wish. So assuming that the car continues to move at constant velocity, then we can predict the position of the car using this particular model, v equal to delta x over delta t. Delta is another Greek letter which is used to indicate the difference or change in something. So delta x over delta t means final position minus initial position over final time minus initial time, whereby we use subscript f to refer to the final state and 0 to refer to the initial state of the car. These are notation commonly used in literature, by the way. We substitute the numbers, a little bit of algebra which I will leave to you guys to work out yourself. We will arrive at the conclusion that 2 seconds later, the car will be found at 5 meter, still maintaining its speed of 2 meter per second, and its course along positive x direction obviously, since we have already assumed the velocity to remain constant. Is this prediction correct? Is the model making sense? Well, experiment will indeed show it is. After all, it is a relatively straightforward problem. If the car does move at 2 meters per second and we do not expect the car to change its speed and direction throughout, then the distance the car travels will simply be proportional to how fast it moves, that is its velocity, times how long it takes to move. But just like every model, it comes with an assumption. That is, the car continues to move at constant velocity. A model is only valid insofar as the assumption is fulfilled. If this assumption is not true, the model is wrong. Then the prediction will also be wrong. In that sense, this is how science, physics included, progresses. One conducts experiment or measurement to gather a set of data, comes out with a model to explain the data, and in so doing, one makes assumption or postulate, if you have heard that jargon before. Put the model to test by trying to make prediction out of it, and run further experiment to see if the prediction comes true. Any accurate prediction will reinforce the validity of the model, until the point it is no longer accurate and one has to modify the model. The cycle goes on, but don't forget the assumption. The model is only working within the limitation imposed by the assumption. Obviously, in our case, this so-called uniform motion model is rather limited. It is only valid when velocity remains uniform or constant. But let's say it is not the case. Let's say that sometimes in between, a force is being applied on the car, pulling the car as such. By the way, don't argue with me why on earth would the car experience such force. Use your imagination. Perhaps it is an attack from one of those giant spaceships in Transformers or Avengers series. Anyway, that's out of the point. The point is, if the car does experience a force and is no longer able to maintain its velocity, will the model still work? Will we still find the car at 5 meters after 2 seconds? Obviously not. The uniform motion model will no longer work because the assumption that the car continues with constant velocity is no longer true. The car can no longer maintain constant velocity because of the pulling force from the spaceship. By gut feeling, in such scenario, you might have expected the car to move something like this. Notice that the car will not straight away get sucked up. It moves forward a little bit because of the initial speed of 2 meters per second it is undergoing. But eventually, the dragging force will slow it down and pull it up. Now, we can make this sort of educated guess because we know 1. The state of the car, namely its current position and velocity, and 2. The force that is applied on the car. Those are all we need. Of course, for exact computation of the car's trajectory, we will need more information like the force strength, its elevation angle, etc. We will learn how to do this computation soon. So going back to our definition of mechanics, if you do not like me to use bombastic jargons like states, physical system, or evolve, mechanics studies how things changes its position and velocity over time. In even simpler terms, mechanics is the study of how things move. I'm well aware that I have been taking too long talking about model, scientific progress, giant spaceship and all, only to conclude that mechanics is the study of how things move. I could have just told you guys right from beginning, but by doing so, I would have done you guys as well as this chapter on mechanics injustice. For unlike physics in O-level when you were just asked to memorize F equal to ma, plug in M, plug in A, then compute F, you didn't ask why F equal to ma, or is F equal to ma the right equation to use in the first place. Here I want you guys to be critical. I want you guys to always ask what the underlying assumption in any physics equation you will see and use in this course. I want you guys to always check and recheck that you are using equation insofar as permitted by the assumption, that you are using the right concept, theory, and model to solve problems at hand. In any physics lesson, mechanics always serve as the opening chapter because it provides framework on how you should study physics and approach physics problem. So here is the outline of what we are going to learn in the next couple of weeks. Under the broad topics of mechanics, we have kinematics and dynamics. In kinematics, we are dealing with situation when the car is already in motion. It may move at constant velocity or changing velocity, but we do not concern ourselves with what causes the object to move in the first place. Quantities such as displacement, velocity, and acceleration are the relevant quantities. Dynamics is an extension of kinematics. Yes, we will still be dealing with displacement, velocity, and acceleration here. But on top of that, we also concern ourselves with what causes the car to accelerate or change its direction. There are generally two approaches on the study of dynamics, by examining the force exerted on the car or the conservation and conversion of energy happening on the car. In this chapter, we will learn how to draw this so-called free body diagram to model the system. to learn to apply Newton's law of motion and the conservation law of energy and momentum in problem solving. I assure you this will be exciting.